So the last topic related to decoding schemes, we'll be covering speculative decoding, which is fairly interesting idea and pretty recent. So here we'll have uh, two LLMs, a large LLM and a smaller LLM, and what they found out that, and it is from DeepMind and Google, both they published in parallel papers and methods which are pretty similar, and they found very similar results also, that they got speed up in generation or decoding with 3 times of what the usual decoding takes or generation takes. So here is the paper if you want to refer to, and they are pretty similar and in terms of method, but so you can go through any of them. Okay, so to understand the speculative decoding, we need to understand the underlying problem. So what is the underlying problem? So when we are decoding, and I'm talking about inferencing, when we are doing inferencing. So let's say this is a large LLM, and I asked it to generate a story. I gave a prompt, or I gave a kind of instruction to generate a story. So what will happen for each word? Let's say it generated 100 words. So for each of these 100 words, for word 1, and let's say it has 100 billion models similar to this, so 100 billion models, 100 billion parameters. So for each of these decoding steps, so we'll generate W1, W2 up to W100. For each of these 100 words which are decoded in forward pass, we need to do computation 100 billion times. So we need to do compute 100 billion times, or 100 billion compute flops will be there, right? So for each of these word decoded, we'll have to do 100 billion computations, and then again 100 billion computations. So in total 100 multiplied by 100 billion computations. So these many computations we'll have to do, and we can, very interestingly, we can omit some of the or many of the computation steps by utilizing the speculative sampling. How? So let's say we utilize this 100 billion model, which is pretty large model, and we need to generate the next word. So the given sentence is Geoffrey Hinton did his PhD at the university, right? So what would be the next word? Next word would be very simple, off, right? So it will take 100 billion compute flops. Then the next word we need to generate is Edinburgh. It will also incur 100 billion compute flops, right? But these two things are not very different. These two things are pretty different, these two words. So generating off, it's pretty straightforward, and it's pretty intuitive that after the university it should be off. But generating the exact university name, whether it should be Edinburgh or it should be University of Oxford, it is very difficult for the model. So not all the model will be able to generate Edinburgh, but very small model can also generate off, right? So this is the whole idea. The core idea is, when you are generating the text, there are some words, they don't require much knowledge injected into the model, maybe LLMs, and they don't need much reasoning like off, but there are some words which require knowledge, and also they require more reasoning by the model. And this example what I'm taking is taken from efficient NLP. Okay, so the model generated Edinburgh, and Geoffrey Hinton did his PhD at the University of Toronto, right? So, but the real thing is the University of Toronto, right? So what happens is, when we are doing this autoregressive decoding, we can utilize a smaller model which we call draft model, right? And then we can have a large model that is called target model. So for generating the text, we can generate the lots of tokens, or maybe many of the tokens from the draft model, and we can feed all those tokens to the larger target model, and it can verify whether this is correct, this is correct, this is correct, this is not correct, this is wrong, right? So if we can do so, we will save the compute. Why? Because this model might be having, let's say, just 10 million parameters. So for each uh, for each decoding step, only 10 million flops need to be computed. So 10 million computations will be there. But in case of the large model, let's say it's 100 billion, so it saved 100 billion here, it saved 100 billion here, it saved 100 billion here, it saved 100 billion here. Maybe this was not correct, so it had to generate, let's say, the next word. So it incurred 100 billion here, right? So it saved a lot, right? So to formalize it in terms of an algorithm, which we have seen in the paper itself, that we have a draft model, which is a smaller model, and in case of DeepMind paper, they used 7 billion chinchilla, and a larger model which is slower, which requires more compute operations in forward pass. So that's called target model, and they utilize 70 billion chinchilla. So the idea is, the draft model speculates in future. So it says that given the current word my, it generates name is Rohan and so on. It generates all those, and there is a target model. It feeds these generated tokens are fed to this target model, and it verifies whether my is correct, name is correct, is correct, maybe the name is not correct. So it seizes that, right? It will go to, so it will kind of go to some another thread where we will discuss what it will do at that time. So the core idea is, in the first step, draft model decodes k tokens, and this k is you need to select. So you need to fine tune k. You need to find the probable value and adequate value of k. So the draft model decodes k tokens in regular autoregressive fashion. So it's pretty simple. In autoregressive fashion, it will generate, and you know what is autoregressive. Then in the second step, we get the probability outputs of the target and draft model to the new predicted sequence. So these generated tokens will be fed to this, and then for each token we will get the probability distribution. So we will get the probability distribution from the target model, and both from the dark. So when we are generating these words in autoregressive fashion, anyway we have already saved the probability distribution for each of these words, right? So we have the probability distribution of the generated words from the draft model. We feed them into the target model. We get the probability distribution for these words from the target model also. Then we compare these probability distribution from the target and from the draft for a particular word, and then based on the rejection criteria, we either select it or we reject that, right? So we'll see what is that rejection criteria. And at the end, if k tokens are accepted, all the k tokens are accepted, the target model generates an additional token, right? So target model will generate additional token which will incur in case of DeepMind's experiment, it will generate 70 billion, it will incur 70 billion computations. So here is the algorithm in terms of visually explaining this. So let's go through this example where we have, let's say, we say that draft model is MP and target model is MQ. And in case of Google paper, they used 7 billion llama and 70 billion, or for an example, for this Meta llama 70 billion and 7 billion. And what we have is, we have, let's say, prefix that is, let's say, the prompt, or maybe the instruction, right? So given this prefix, given this input, the model, and we are talking about so we are talking about MP. So the draft model generated x1, and then given this prefix and x1, in autoregressive fashion, the model generated x2, and so on, model generated x5. So these 5 tokens are generated by the model, which is a draft model. And then, to recap, we have this draft model which generated 5 tokens given the prefix. And then what we need to do, all these draft models, we need to pass it to the target model, and then you will get the, and then, yeah, additionally this target model generates Q6. So generate this X again. So the draft model has generated these 5 tokens. The target model has generated this 6th token, right? So that's what target model will do. So what we'll get here, the same things are copied here. So for an example, let's say the draft model generated dogs, loves chasing after cars, right? And this target model, we pass these tokens again to target model. It gave the probability to dogs here, to love to this much, and to chasing this much, and after this much, and so on, right? Now we'll go to the next rejection sampling step. So in the rejection sampling step, what we need to see, we need to find out whether the generated tokens by the draft model are appropriate or correct or not. So in this case, we can see that, let's say, dogs, which is okay by the target model, love, which is okay by the target model, but chasing, let's say the target model says no, chasing is incorrect, it should be sleeping, right? So what will happen, we will just take these two, and the rest of the tokens we will kind of omit or prune, and then again the draft model will generate something, right? So this is what these are the conditions. So when Qx is greater than Px, which is written here anyway, so we can see that Qx is greater than Px. Yes, this is correct. Qx is greater than Px. Sorry, Qx is greater than Px. Qx is greater than Px. No, so here the Px is greater than Qx. So in case of Qx is greater than Px, these will be selected, and when this condition is not met, if the Qx is less than Px, which is in this case Qx is less than Px, then this will not be selected, right? And then what will happen, then we will accept this with a probability of Qx divided by Px. So we'll compute this value Qx divided by Px. So specifically 0.8 divided by 0.9, and whatever be the value, with this probability we will select this chasing or not, right? So what will happen in worst case? What will be the worst case? That, let's say, these tokens were generated by the draft model, and first token itself, let's say this value was not 0.9, it is 0.6. So now the Qx is not greater than Px. So in this case, we will not select even the dogs, and left alone the rest of the words. So left of the words will also be pruned. So in this case, how many tokens will be generated by this model, speculative sampling? So it will only one token, which will be generated by the target model. So in all the cases, when you pass the draft model, the words or maybe tokens generated by draft model, you will feed into this big target model. It will not only check these words, all these words, but also it will generate an additional. We had seen that there is additional token it will generate, right? So x6 it will be generating. So in case the first word itself is rejected, then model is left with this excess. At least it will generate one target, right? So it says that it is rejected, but it will generate some the word. In case the best scenario or best case, when all the generated word by the draft model are accepted. So let's say this is accepted, and this is also, maybe it is 9, it is accepted, it is 9, it is accepted, it is 8, it is accepted. So all of them are accepted. In that case also, so k tokens are accepted from draft model, but one token which additionally generated by the target model will also be there. So there will be in total k plus 1 tokens. So this is from the original paper. They have shown that when k is equal to 7, when k equal to 3, and originally what is the time. So when they wanted to generate for let's say for a sample, they want to generate 100 words, it took these many times. When they took k equal to 3, the time reduced to this much. When they took k equal to 7, the time reduced by this much, right? So here is the illustrated example where Japan's benchmark, and these green things are generated by the draft, and then the blue things are generated by the target model. So it says Japan's benchmark and then generated bond, which was incorrect. So model generated N. So next time what will model start with? Japan's benchmark N. This will go as a prefix, and then the draft model will generated these I, K, K, E, I. So Nikki, so full word, and then 22, and then model generated something which was not correct. So it generated 5, and so the new prefix will be this much for the draft model. Then draft model generated index rows 22, but it generated something incorrect, or maybe ended there. Then target model generated 6, and it goes in. Then the draft model generated 69, and then the target model generated points, and so on. And towards the end token was generated by the draft model itself. So this is how it kind of this speculative decoding worked. So in terms of results, if you can see that the DeepMind team, so they had 2 papers published, so one from Google Research and DeepMind, and pretty similar idea. The idea is same. They found out that they got 2 to 2.5x speedup, and compared to the original without speculative decoding kind of model, and they suggest that the k value should be between 3 and 4. On the other hand, Google Research says that it should be between 3 and 7, and they got almost similar kind of speed up to 3.4. So yeah, so this is it, and in the next lecture we'll be seeing some of the problems of not just decoding but the natural language generation when it comes to LLMs. So you might have heard of some of the terms like hallucination or non-faithful summarization and so on. So what is the problem there? So model is generating the text, or maybe answer, or maybe in question answering it is generating answer, or maybe in summarization is generating summary for your document, but that summary is not faithful, or that answer is not correct. So why model generated a wrong word, or maybe the wrong sentence altogether? That is the issue. and that issue is called hallucination. So model might be hallucinating, and it's not kind of it's able to figure out what would be the correct answer or what would be the correct summary. So we'll be discussing about that. And another challenge is, let's say once the model is trained, and you might have heard of that these models like ChatGPT and Llama and other popular LLMs, they take lots of money and they'll take lots of effort and time to get trained. So because of this so much baggage they have, you cannot retrain them like after after a while, or after a month, even after a year. So what happens because of that? Because models visibility or vicinity of seeing the data is limited, because you have, let's say, a ChatGPT was trained for data till 2022, but what happened after 2022, those kind of information and cues and the documents are not seen by the ChatGPT, so it cannot answer that. And if you ask such a question to the large language model or ChatGPT kind of systems, they will hallucinate. So they don't know the answer because that is not in their pre-training memory. So how to get the things which are maybe updated or which are pretty recent, how to kind of inject those knowledge into the model and generate something which is appropriate or something which is correct, is the problem. So we'll see and discuss these two and maybe other issues, and we'll see one of the solution, which is called retrieval augmented generation, in the next class.